thumb finger is the one which gives the direction of a force. Your middle finger gives the direction of current. Then the perpendicular one, that is the index finger, gives the direction of the magnetic field. How do you define force per unit length of a conductor in this case? Force per unit length of a conductor is directly proportional to the product of the current of the two conductors. Each and every turn has got certain magnetic field, and net magnetic field is vector sum of all the magnetic field of this solenoid. Hello everyone, I am Vrinda, Faculty of Physics from Vidhyaashram Pre-University College, Mysuru, welcoming you all to session 4 of chapter 4, Moving Charges and Magnetism. In today's chapter, we are going to study about the right hand rule, Fleming's left hand rule, as well as something about solenoid, toroid, what is meant by that solenoid as well as toroid, as well as the force which is acting between two conductors placed parallel to each other. So now we are checking on to right hand rule, or else it is also called as a grip rule. So it is a right hand thumb rule. So I want all of you to just hold thumbs up in your right hand so that you can observe the red color direction as well as the blue color direction. That is, the curled finger gives you the blue direction and the thumb finger gives you the red direction. So what does this right hand thumb rule suggest? It is nothing but, according to this right hand thumb rule, the thumb finger gives the direction of the flow of current. That is, this red mark gives the direction of flow of current, and the curled fingers gives the direction of the magnetic field. So the current as well as the magnetic field both are perpendicular to each other. That is, the thumb finger, the direction of the thumb finger is upward. So upward there is a flow of current when you hold a conductor, and the curled fingers is the conductor's magnetic effect due to the current which is passing, that is current which is flowing upwards through this thumb finger. Got it? So that is all about your right hand rule, which is also called as grip rule, which we will use in further cases. Okay. So next we are going on to Fleming's left hand rule. So I want all of you to just hold your left hand in such a way that your thumb finger, your index finger and your middle finger, all three fingers are perpendicular to each other. You have to hold your fingers in such a way that your thumb finger is perpendicular to the index finger as well as for the middle finger. Again, your index finger should be perpendicular to your thumb finger as well as the middle finger. Same, your middle finger should be perpendicular to thumb as well as the index finger. All the directions should be perpendicular to each other. Then how do you give this? So this is the Fleming's left hand rule. Your thumb, index as well as the middle finger. So thumb finger gives the motion, okay, or the force. Okay, thumb finger is the one which gives the direction of a force. Your middle finger gives the direction of current. Then the perpendicular one, that is the index finger, gives the direction of the magnetic field. Your middle finger gives the direction of the current and your index finger gives the direction of the magnetic field. In that case, your thumb finger will give the direction of the force which is applied. So this is all about your Fleming's left hand rule. I hope you're clear with the right hand rule as well as Fleming's left hand rule. Now we are going on to the topic called as solenoid. So in solenoid, it is a long insulated wire is wound in the form of a helix and is closely packed. Each turn is said to be closely packed to each other. That is, this is a helix of the insulated wire. Okay. So the solenoid, when the current passes through the solenoid, the net magnetic field is the vector sum of each and every magnetic fields of the helix or the individual turn. Each and every turn has got certain magnetic field, and net magnetic field is vector sum of all the magnetic field of this solenoid. Okay, so this is actually used in order to calculate the uniform magnetic field. It is used in order to obtain the uniform magnetic field. Okay, so this is a solenoid. Similar way, so the solenoid can be considered in case of bar magnet. In next chapter, you will study much more about this solenoid concept. Okay, so now the solenoid has got certain magnetic field, and what is the equation of magnetic field which is given here? That is mu naught into Ni. So this is the magnetic field in case of the solenoid. This is the equation to calculate the magnetic field within the solenoid when certain amount of current passes through it. That means when there is a presence of current, there is presence of magnetic field. Okay, so that's all about your solenoid. They have not given much of the derivation because it's excluded from your syllabus. It's only the expression what you have to study. And next we are going on to the toroid. So how exactly you find this toroid? Toroid is nothing but it's same as that of the helix. Again, in case of toroid, we have a long wire is said to be wound. It's donut shape. Okay, there is a donut shape there, that is the circular shape where exactly the long wire is wound completely in this form. Okay, so this makes a toroid. Okay, this acts same as that of the solenoid. Both are one and the same, but solenoid is a long straight shaped wherein it resembles the bar magnet, wherein in case of toroid it gives a circular in shape. And the magnetic field within this toroid can be given as B is equal to mu naught N and I. It is same as that of your previous solenoid as well. Okay, so again solenoid as well as toroid, they have not given an derivation for this expression. It is only to mention the expression. You need to know what is meant by solenoid, what is meant by toroid and its magnetic fields. Having these concepts, let us just get into a most important derivation on the exam point of view. That is, from this chapter you have an important derivation, that is, derive the force between two parallel conductors which carries current. So we need to know what is the expression for the force which is experienced by a parallelly placed conductor which has the current I. So I just consider two conductors on which there is a presence of current. Call it as I1 and I2. So now let the conductors be named as P and Q. So PQ are the two conductors which is parallelly placed and through which the I1 and I2 current is said to be moving. So the distance between two conductors, call it as D. Let D be the distance between two conductors. Okay, so this is just the description. Whichever I have told verbally now, those are the description. So now starting on to this equation, it is like the force between two parallel conductors carrying current. We need to see the force between two conductors which is parallel to each other. So before that, we need to know what is that force which is acting. That is we just check when there is flow of current, there is a magnetic field which is produced as well as there is force. That is, we have studied this in the Fleming's left hand rule, correct? So now it is like, if suppose you are checking the magnetic field, that means the first conductor, the conductor P, carries current I1 whose magnetic field is at the site of Q. So the current I1, the conductor which carries current I1 experiences a magnetic field B1. That is the first conductor. No. So if in first conductor the current is I, we call it as I1. And the same conductor experiences a magnetic field in the site of Q, call it as B1. So when that is the case, I'll just give the B1 is experienced over here. Since it is perpendicular, we are drawing the normal conditions to the below conductor. Okay. So now Why I have placed my B1 here? I can even place here. Yes, I can place anywhere else I want. But since I'm considering only the line segment which is present over here, I'm drawing my B1 here. That means I1 is experiencing a magnetic field of B1 at the site of Q. This is the condition. Okay. So at that time, how can you give the magnetic field as? The equation is the magnetic field due to current I1, you have B1 is equal to nu naught by 4 pi I1, that is 2 I1 divided by D, that is the distance. Okay, so this is B1. Next, we have got B1 and now we are taking only a small line segment on the site Q conductor. So now the force due to conductor P, that is the force due to conductor P, that is the first conductor, is given on the site of Q itself, but it is said to be perpendicular to Q. So let us just give the perpendicular direction. So it is F1 towards the P conductor. So it is, you have F is equal to I L B sin theta is the general equation. But applying for this, you have F1 is equal to, what is I? I is said to be I2 because F1 is acting on the second conductor where the second conductor has got the current I2 and it is L. L is the length, that is the length of the segment I am taking, capital letter L, so it is L. B1, this is considered as B1 because the magnetic field experienced is B1 and sin theta. On substituting, you have I2, L, B1 is nothing but nu naught divided by 4 pi 2 I1 into sin theta. This is divided by D. So you can rewrite it as nu naught by 4 pi 2 I1 I2 divided by D into L sin theta. And you know, the force is perpendicular to the plane. So theta makes 90 degree. So the sin theta is nothing but 1. This is since theta is equal to 90 degree. That means sin theta is equal to 1. So you have F1 is equal to nu naught by 4 pi 2 I1 I2 divided by D into L line segment. You can consider this line segment as a unit line segment, whatever you consider. Okay. So that is all about your one conductor I1's influence on the Q conductor, that is the second conductor. Now back again we are checking on the magnetic field due to I2. We are checking one by one, but the process is acting simultaneously. When the current exerts a force on Q, then the Q conductor also exerts certain force on the conductor P, on the current I1. Okay, so now it is the magnetic field due to I2. How is that we are writing? So magnetic field is the second B2 magnetic field, which turns out to be in this direction because we consider a certain line segment and the line segment is of the length L and this is said to have B2 magnetic field. At this condition, B2 is equal to nu naught divided by 4 pi, and what is the current here? It experiences I2 current divided by the line distance between the parallel conductors is said to be D. And next is the force. The force due to Q on site of P is given as F is equal to, this is a general term, I'll not repeat this again. It is the force experienced will be downwards now, that is at 90 degree. So both are facing each other in the opposite direction. So when that is the case, it attracts, the two conductors tends to attract each other. So it is F2 is equal to I L, that is I means in the sense it is I1, it is experienced, F2 force is experienced on I1 and the length segment L you're taking, and it will be B2 sine theta. Again sine theta, since theta is equal to 90 degree, sine theta tends to become 1. So it is F2 is equal to I1 L. What is B2? It is nu naught by 4 pi 2 I2 divided by L. So on equating nu naught by 4 pi into 2 I1 I2 divided by D into L. This is the force F2 due to the conductor Q at the site of P. So you have F1 as well as F2 equation. So both are acting opposite to each other, because of which they tends to attract each other. That is, there is attraction between the two conductors which is parallelly held. So therefore, the force per unit length of the conductor can be given, that is force per unit length. It can be equated as, force per unit length of a conductor can be equated as nu naught by 4 pi into 2 I1 I2 divided by D in both the cases, because L comes down, force per unit length of a conductor. So how do you define force per unit length of a conductor in this case? Force per unit length of a conductor is directly proportional to the product of the current of the two conductors, product of the current of, because other rest of the things are constant terms. So force per unit length of a wire is directly proportional to product of current of the two conductors and inversely proportional to distance between them is the concept here you study in case of the force between two parallel conductors which carries current. Okay, so this is one of the important derivation for 5 marks, wherein you will have to draw this as well as give the description, then step by step first find the magnetic field due to current I at the site Q, then again force also, force due to the first conductor is acting on the site of Q itself, so then find the force by using the force on the current carrying conductor equation which was derived earlier. So for that we will just substitute, you will have to know F1 is acting on the second conductor where current is I2 and its lines segment whatever we are taking, and B1 that is due to the F1, and sine theta. Since the force is perpendicular, this construction, that is the magnetic field and force is given perpendicular to each other with respect to the current by using Fleming's left hand rule. That concept you will have to use here, and again repeat the same concept for the next conductor. Since both are same, you can just give force per unit length. That means F divided by L, force per unit length. Length you are taking it from your right hand side equation towards the denominator, so that you will get equation like this. So concluded by saying force per unit length of a wire is directly proportional to product of the current elements and inversely proportional to distance between them. So now having the same concept, we are just defining ampere. So how do you define an ampere in case of moving charges and magnetism concept? That is the magnetism concept. You have force per unit length of a infinitely long conductor which carries current is given as nu naught by 4 pi into 2 I1 I2 divided by D. So this equation can be considered for this ampere, define ampere. So you have force per unit length of a wire can be, if suppose it's your current I1 and current I2 is said to be 1 ampere, and D is at a distance of 1 meter, then you can define this 1 ampere as force per unit length of a wire is equal to nu naught by 4 pi. Substituting, you have 2 into 1 divided by 1. So you know that nu naught by 4 pi has got a value, that is nu naught is equal to 4 pi into 10 to the power of minus 7 Tesla meter A inverse. So having this, you just equate, you have mu naught by 4 pi. So what remains is 10 to the power of minus 7. So you can rewrite this as 10 raised to minus 7 into 2. So F by L, force per unit length, is can be given as 2 into 10 to the power of minus 7 Newton meter inverse, because force is given in Newton, L is meter, so meter comes out, Newton meter inverse. This is all about your ampere. Okay, that is all about today's session. In today's session, we have studied about the solenoid, toroid, right hand rule, Fleming's left hand rule, force between two parallel conductors, as well as having the same concept, we have defined an ampere. That's all for today. Let us all meet in our next upcoming classes with the winding up of this session. Until then, have a good day. Thank you.